So welcome, my name is Doug Schutten and I'm the CTO at Ideon Technologies. And I'm delighted to have the opportunity to present one of our first published case studies using our borehole muon tomography technology for mapping uranium deposit at considerable depth in the Athabasca Basin. So Adion Technologies uses the energy from supernova explosions in space to provide 3D imaging down to about 1 kilometer beneath the Earth's surface. And there's a wide range of scales in this problem. We're using massive energy explosions from light years away and providing imaging across kilometers of rock using particles that pass through a detector in the speed of less than a nanosecond. So a very interesting application of a passive radiation source to map subsurface density in high resolution. And it has a very good analogy to X-ray technology that we're all familiar with in the medical space. So just as X-rays are an attenuation-based technique to map density structures inside the human body, but basically placing an X-ray source on one side of the body and observing the rate or the attenuation of X-rays as they pass through the body. And where X-rays are attenuated, we infer high density. Where they're passing through unobstructed, we infer low density structures. And we can use multiple X-ray images with computed tomography to derive 3D models of dense structures within the human body, allowing for keyhole surgery. In the same way, we can use cosmic ray muon radiation or radiography to enable geologists to see inside the Earth and produce 3D models of subsurface density by mapping the attenuation of cosmic ray muons as they pass through the Earth from above. So a muon is a naturally occurring subatomic particle that's created as a result of supernova explosions in space. These supernova explosions eject very high energy protons and helium nuclei that pass through intergalactic space and eventually impinge upon the upper atmosphere of the Earth and initiate nuclear fission effect. And out of those interactions come a slew of secondary particles, the majority of which are absorbed very quickly or decay really quickly. Such that at the surface of the Earth, about 95% of the resultant radiation spectrum is comprised of muons. These are passing through the surface of the Earth from all angles, across time and all over the Earth rather uniformly. So they lose energy as they pass through matter, and they lose energy at a rate that's proportional to the density of the material they're going through. And so in higher density material, they lose energy at an accelerated rate and are eventually stopped. And so what we can observe then is the rate of muons that survive to some depth, or the directional muon intensity from all directions, and develop essentially a map of muon attenuation, which is essentially a map of average density between a detector located under the ground and each direction to the surface. This develops a two-dimensional radiography, or like an X-ray image of average density in the Earth. And by combining multiple such images, we can develop a 3D density profile, and that process is muon tomography. So just as a point of reference to orient yourself in the relative rate of abundance of muons, they're passing through the Earth's surface at about once per minute for every square centimeter, or about once per second through an area the size of the top of your head. So the way we use this for mineral exploration, resource delineation, and a host of other applications that subsurface density mapping are applicable to, we deploy sensors in multiple boreholes, and we can deploy up to 10 detectors in a single borehole in a daisy chain configuration. Each borehole detector will image or collect muons passing through it in a wide field of view of about 120 degrees up to the surface. Within this field of view, any muon that passes the detector is recorded, and its trajectory, its direction is recorded as well. And so we know where the muon came from. And over time, we build up a profile of where muons are coming from and where they're preferentially not coming from. And that's essentially a map of average density in each direction. That develops a single radiographic image for each detector. And so from a single detector location, we can actually define the location of a dense anomaly, at least in a directional sense from the detector. So by combining multiple detectors, each with its own field of view, we can use triangulation or tomography to essentially develop a 3D density model of the subsurface, which has great applications for mineral exploration and resource delineation, to name a few. So I started with an analogy between X-rays and cosmic rays and their use for mapping internal density of structures. Muons are very similar to X-rays in the sense that they're both an attenuation-based technique, but there's some key differences. The first is that cosmic ray muons can penetrate through hundreds of meters of rock, even down to below a kilometer. And the spatial resolution is on the meter scale. So with cosmic ray muons, we can resolve structures that are in the 0.1 to 0.2 gram per cc density contrast with respect to the country rock, depending on the spatial resolution we're trying to achieve. So there's a trade-off between spatial resolution and density resolution, of course. Because it's a passive source, natural background, there's no safety implications, there's no operational implications. It's a ubiquitous radiation source that's for free. But it has also an implication on the imaging time. And because it's passive, it can take weeks to months, depending on depth, to record sufficient data sets to resolve structures with statistical significance. And so this is a tunable thing based on the number of detectors, since it's basically an intensity measurement, which is a number of muons per unit area. By scaling up the number of detectors, we can linearly reduce the amount of time. That is to say, if we double the number of detectors within an area of interest, we can half the amount of time needed to record a sufficiently sized data set. We developed 3 generations of detectors at Ideon. We started with a V1 gallery detector. That's been a very valuable tool to be able to prove the technology and has been useful for in-mine surveys, looking for extensions to known ore bodies and also sort of near field exploration. We also developed a V2 borehole detector, and this was about the size of an oil drum, which was really serving 2 purposes. One was a stepping stone to the narrow form factor borehole detector that we envisioned very early on as being required to really get this technology's use in mining, but also for a geotechnical application where we were able to install it at relatively shallow depths, whereas creating a hole of that aperture was not economically infeasible. And so we were able to use that detector quite successfully. But then in 2021, we finished development of our V3 borehole detector, which represents a 50x miniaturization over the original detector, but maintaining the same intrinsic tracking resolution, that is to say imaging resolution, in the detector. So muon tomography is a wide range of applications, basically wherever there's a density contrast to something of interest in the subsurface, it can be used to map that with high resolution. In terms of commodities, there's of course a range of commodities that have a significant density contrast depending on the deposit types. And we've had published case studies across a couple of these. And the focus of this talk today is on applying muon tomography for high-grade uranium deposits, such as those found in the Athabasca Basin. It can be used in early stage exploration all the way through to resource delineation, and through depths down to a kilometer underground. And because of its intrinsic kind of passive nature, it can be used in areas where other geophysics technologies can be confounded by conductive cover, by cultural impacts, such as power lines and infrastructure, and also where there's, say, blasting or mine operations that creates noisy environments. Muons are basically impervious to all of these effects. And so there's a good use for muon tomography, especially in mine applications. So I'll switch gears now and talk about the McLean Lake trial, which was the world's first borehole detector deployment in muon tomography. And this was at a mine operated by Orano. And we were using an existing ore body as a sort of a field test of our ability to image compact uranium deposits at greater than 200 meters depth in the Athabasca Basin. So the Orano partnership began already in 2017 when we used our V1 detectors to image the Zone 4 North deposit at McArthur River with our detectors situated at depths of about 600 meters underground. So this was a project that was led by Orano with support from Cameco. We published that in the American Geophysical Union. It was a very compelling case study demonstrating the ability for muon tomography writ large to be able to image these ore bodies. We then did a modeling study with Orano to understand how we could use that technology in a borehole context across a wide range of exploration opportunities, and really worked on optimizing the parameters that would be required to make that kind of detector successful. Out of that came a project to develop the detector and then to deploy it in a field trial. And the place we settled on in the end for deployment and for field testing was at McLean Lake. So this was a project that was supported by Orano and also through Eureka, which is a France-Canada funding cooperative. We developed the HQ-sized borehole detector and deployed it there. And today I'll present the results of that first field trial and show the quite nice ability to image a very, very compact ore deposit. So just harkening back to the 2017 demonstration, this was again at McArthur River at about 600 meters depth. And we installed 4 detectors below and off to the side of the deposit. Orano and Cameco had, of course, studied this deposit in great detail before we arrived on site. But we performed the analysis completely blind. That is to say, we used no geological information in understanding or interpreting the results from the muon tomography data. On the left, you can see a simulation where we took the locations of the detectors and developed synthetic muon tomography data, assuming that the deposit, shown in this kind of orange shell, had a uniform density contrast with respect to a completely uniform background density. And you can see the ability for us to be able to reconstruct that deposit with quite high resolution with the density slice from the muon tomography synthetic inversion shown. If you look at the field data, we see quite good correspondence, and we can see how the high density shell from the muon tomography data corresponds very well to the known mineralization. What was interesting also is that the field data saw that the barycenter of density was somewhat shallower in depth than predicted from the simulation, if we assume in the simulation that the ore body has a uniform density. But in fact, when we look at the drill data in some detail, we see that there's considerable heterogeneity within it, leading to lobes of higher density. And in fact, that matches really well with the field data. So not only were we mapping the deposit writ large, but also mapping the density contrasts within it. So based on that successful outcome, we, of course, moved at haste to develop a borehole system. Again, a miniaturization of 50x, which was no small feat. But we developed an HQ-sized detector. So it's about 89 millimeters in diameter, 3.5 meters long, 4 meters long if we include centralizers. So roughly the length of a single drill rod, over which the borehole is assumed to be linear. It consumes quite low power, considering the fact that it's got very, very fast electronics to be able to resolve muons that pass through the detector in less than a nanosecond. And we are able to deploy this in quite harsh conditions with non-operating temperatures from -30 to 50 and operating temperatures within a reasonable range for most borehole applications in mineral exploration. So it's submersible down to about 1 kilometer of water pressure, but still maneuverable to be able to be manipulated on surface and deployed. So you can see some sort of intrinsic characteristics of the system from lab testing. One is you can see a comparison of the muon flux at sea level between theory in green and the data. And you can see very, very good correspondence, and the detection efficiency for seeing muons that pass through the detector is about 95%. And we also have good spatial resolution. So it's a 1.5 degree angle resolution on each muon passing through. And that translates into about a 2 meter spatial resolution from a distance of 100 meters away. So the intrinsic imaging capability of the sensor is very good. So the McLean Lake trial was situated as shown in this image. We deployed 6 detectors down a single hole, down to a depth of about 290 meters. The mineralization of interest is shown in red. I'll get into more details on the structure of that mineralization, but it was embedded within a complex geology with significant alteration around it. And we are also kind of off to the south of an open pit that had been since backfilled and filled with water. And our field of view projected up to the surface, as you can see in the bottom right, was significant from a depth of 290 meters. So from this set of detectors, we were imaging a large volume of rock indicated by the field of view shown from the bottommost detector. So looking in more detail at the survey configuration, you can see the situation of the detectors down to 290 meters, and in particular, noticing that we deployed them in a way that avoided the area of highest radiation, background radiation that was pre-logged during the performance of the drill hole. However, even though we worked to avoid that radiation zone, the radiation counts there were not even that high, and we're pretty confident that our detectors would have been able to operate just fine within that zone, given our ability to reject non-muon backgrounds in the system. It's also worth noting that the high-grade ore pods embedded within that mineralization structure are minuscule. You can see them highlighted in red. So these are the ore pods that are sort of greater than a few percent uranium ore, based on prior knowledge from drilling and exploration in the area by Orano. But it's surrounded by a sort of trace mineralization halo of somewhat elevated uranium mineralization. But if we look just at the high-grade ore pods and forward model that, we'd see that the expected statistical significance over even a significant exposure time of the detectors was minuscule. You can see the sort of shadow of density cast by those ore pods on the radiographs for the detectors. And what's worth noting is that the sort of expected statistical significance from all of those synthetic data is significantly lower than the threshold that we'd ideally have to be able to robustly image a structure. However, if we look more broadly at the mineralization shell itself, the whole structure represents about a 0.1 gram per cc contrast over the surrounding rock, which is sort of at the threshold of our capability for mapping density contrast. When we look at that whole structure, though, we do see in the forward modeling and simulation that we would expect to be able to resolve it with some resolution. So when we run our forward model and then invert that synthetic data, we get a reasonable representation of the mineralization shell. It's worth noting the size of the structure, though. If we would run this through a ground gravity simulation and look at the size of the signal we'd expect to see, it's a 0.5 microgal anomaly, so way below the threshold of even a very top-notch gravimeter available in the market. So quite a small, subtle contrast, but a good test bench for testing the technology, also because of the significant alteration in the area. So we ran the detectors for a period of time, close to about 6 to 7 months, and we developed a sort of deployment dashboard. We installed the detectors and connected them over a 4G link at the surface to our cloud server and continually ingested data over the whole period of the survey. During that, we could monitor the incoming data, we could monitor the detectors, intervene, recalibrate as needed, and also look at the radiographic data from each detector as it emerged over time. Out of that came the ability to then develop a 3D model from those 6 detector set data sets. First, looking at the left again, by way of reminder, is the sort of forward model of the density structure. And in the forward model, what we've done is we've assumed that the background density is uniform, and we've embedded within it an assumption for what the mineralization structure would look like. We run that through our forward modeling and then run a inversion or tomographic reconstruction on those synthetic data. We can resolve the structure to reasonable density resolution and reasonable spatial resolution, especially if we look at really the highest density elements of the inverse model. If you look at the right, you can see the inverse model derived from the field data. You can see a couple of things that are really worth pointing out very early on. The first is that at a high level, we've been able to reconstruct the density contrast presented by the mineralization structure with pretty good accuracy in terms of spatially locating the core of the density contrast. Another thing that's worth noting is that there is a significantly lower density anomaly both below and above that structure, and that corresponds very well to the known alteration structures in that area. What's also worth noting is that we see a high density anomaly also towards the open pit, and that's not surprising given the fact that the open pit was assumed to be filled completely with water, but in fact, we know that there was significant backfill of mine waste and other material over time in that open pit. And so there's our assumption of it being filled with water is an assumption of lower density than is actually there. So when we map the anomalous density, we see enhancement of density in that direction, and we also see an enhancement of density in the direction of the mineralization. Looking again at that structure, the same kind of representation, but now also including an overlay showing in semi-transparent 3D shape that corresponds to the alteration or the altered rock around the ore body. And you can see how that conforms fairly well with the location of these low density anomalies that we're seeing above and below the mineralization structure. So that is quite interesting because not only we're mapping then the mineralization, but also mapping the alteration halo around it. Here's looking at the same data, but now represented in 3D and allowing us to see how these shapes correspond to each other in fully 3 dimensions. And you can see how the mineralization structure has more complexity than what's in the forward model. But again, fairly good correspondence, and certainly from a targeting perspective, being able to image where the anomaly is and then to drill towards it to really measure the grade directly would be a great advantage in early or mid-stage exploration. Here's again looking at the same, but now sliding a slice or a section view of the density structure from north to south. And you can see again how that conforms quite well to the mineralization shell, and also how we're seeing the enhancement of density within the open pit off to the north. I'll just run that through again. So in summary, for this first field trial of borehole muon tomography in the world, I think it's a proof that borehole muon tomography delivers high-resolution 3D subsurface density data. We see the key signatures in the data that we hope to see. The geological trend and the alteration halo are clearly seen, and the strong evidence of the mineralization halo isolated from the rest of the geology. So the 3D reconstruction maps well to the expected results, especially given the relative paucity of prior information. And it's worth noting again that this analysis was done completely blind. That is to say, we only used muon tomography data in the 3D density reconstruction, constraining that inverse model with the sparse drill data that's available in the area, including the drill data that was acquired in performing the hole within which we deployed the detectors would add value as well. So the first case study ever demonstrated the ability to build detectors, deploy them, collect data, and use that data to derive a 3D density map of the area of interest. So huge thanks out to the Orano team that supported this project with great patience, with great interest, and also good advice. And we're also happy to report that as of this time, we've deployed many systems now around the world, and this first field trial has really been a stepping stone to getting this technology in the hands of many customers who can derive great value from mapping subsurface density structures with high resolution. So thank you for your attention, and feel free to reach out if you have any questions, comments, or if you're interested in joining our team.